Okay, so we will start now. And people in the back, if you can come forward. Okay, so our first speaker for the day is Camille Bilodeau. Dr. Bilodeau has a PhD in chemical and biological engineering. She received the Lawrence Livermore Advanced Simulation and Computation Graduate Fellowship. She did a postdoc studying machine learning for molecular design in Clav's Jensen Group at MIT. And she is currently an assistant professor in chemical engineering at University of Virginia. And her group explores the intersection between AI and molecular simulation with the goal of designing new molecules and materials. So without further ado, let's thank the speaker for the day and give her a round of applause.
Thank you for that introduction. Are my slides coming? There we go. Cool. So today I want to tell you a little bit about generative models, but since we've already heard kind of a lot about generative models for a lot of different applications, I do want to kind of put my own spin on this in terms of the things that I've focused on using generative models for, and that is thinking about applying generative models to the specific problem of molecular discovery. So one of the things that I've been enjoying so far about this summer school is that this has been a really fun opportunity to meet people who kind of lie at this intersection between being kind of ML, AI people and people who maybe are a little bit more educated in the kind of chemical sciences, chemical engineering, biological sciences. And so today I'm hoping to kind of attack this question of generative models for molecular discovery from the perspective of someone who, on one hand, wants to use the best algorithms for the problem, but on the other hand, maybe doesn't work on problems that are as pristine as I feel like we sometimes see in the AI literature. So to start, I was thinking about what are the different sections that I want to talk about related to generative models for molecular discovery. And so the first is that I want to start off by just talking about the mechanics of how do we actually employ AI to generate molecules. Then the second section, I decided to title The Science of How to Discover Molecules. So basically, how can we think about casting the question of molecular discovery as a well-defined mathematical problem? And then finally, because as I will probably say many times during this talk, it's never really quite so simple as how we mathematically define it when we actually need to be able to make a molecule, put it in the real world and use it for something. A lot of the times there's certain things that start to get messy. And so the last part of this talk will be a little bit more about the art of how to effectively discover molecules using generative AI. Okay, so let's start with the mechanics. So we've already heard about this from a number of different speakers, but I'm going to recap it anyway. So what is a generative model? So the goal of a generative model is to learn a distribution from some training samples and then basically draw new examples from this distribution at test time. And so if we think about this for maybe a really simple one-dimensional distribution, here maybe you can envision a scenario where we're going to train our model on these blue data points, and then the green data point is going to be the example that we're drawing out at test time. But of course, for one dimensions, this is pretty boring. What's more interesting is when we start to think about these higher dimensional spaces where we're maybe able to generate more kind of complex objects. And so this is where, you know, in the earlier 2010s, people were focused, I guess throughout the 2010s, people have been focused a lot on AI for image generation, but toward the end of the decade, we saw more AI for molecule generation. And so basically what we're doing here is we're generating examples from a high dimensional distribution. We have a decoder that's able to take some sort of latent space representation and turn that into whatever the object is. And so in that way, these are kind of generative modeling problems. Now, importantly, we're not going to just generate examples at completely random. And so if we do that, we wind up with something that maybe looks like this. So if you read papers, again, from that decade, you might see these really terrible examples of pictures and terrible examples of molecules. And so as a human with intuition, you know those pictures of faces are not good examples of faces, right? They fall off the distribution. And so again, the goal of a generative model is really to learn that distribution and then pull examples. In the case of molecules, though, especially if you're not actually a chemist, you might look at these and say, you know what, I'm not 100% sure what it really means to be a good molecule. And so one of the things that, I think of when I think of what constitutes a good molecule is stable, and that's going to satisfy valency and these types of things that we might expect of a typical molecule. But we'll get back to that in a few slides. Okay, so how can we generate molecules? So before we answer this question of how to generate molecules, we need to kind of all agree on what is a molecule. And so we've already talked a little bit about in this machine learning summer school, the different ways that we can represent molecules. And so the way that we're going to generate them is going to depend on the way that we choose to represent them. So if I asked you to draw a picture of a molecule, the first way that you'd probably do it is by representing a molecule as a graph, right? So here, nodes are atoms and edges are bonds. And so if you asked any high school or college chemistry student to just draw new examples of molecules, this would be the representation you'd likely start with. But of course, we have other options, right? So another classical method for representing molecules in the machine learning community is string representations. So we can represent molecules as either smiles or as selfie strings. And there are probably other representations, but those are some of the dominant ones. And then we can also think about representing molecules in 3 dimensions, either as coordinates or point clouds. And there are a few different ways of doing that. And so the way that we're going to think about mathematically generating these different things is going to depend on which of these representations we choose. And so, for example, for strings, this is fairly straightforward, right? We can borrow essentially tools from the natural language processing community to generate strings, basically just treating molecules as words. So these would be things like recurrent neural networks, transformers. And I won't get into the nitty-gritty details of these architectures themselves, partially because we've kind of already talked about them, and then also because there's loads of blog posts on them. So you can read on that if you like. On the graph representation side, it's a little bit more tricky, right? So there are a few different types of techniques here. I'm kind of binning them into what in my mind are 2 main categories, non-autoregressive and autoregressive. So when we think of graphs, what we're really imagining is maybe an adjacency matrix, which is going to be n atoms by n atoms. So it's basically telling us which of our atoms are bonded to each other. And then our node features. So this is going to be number of atoms by the number of features. And so, and in theory, we could also have a bond features matrix. And so think about generating graphs is by saying, let's just generate initially this node feature matrix. And I'm going to grab a little laser pointer here. We could first generate these node features. Say, okay, I've got all my atoms. How should they be connected to each other? And so this is effectively going to be a one-shot method of generating a graph. What is, I would say, more common within the molecular generation community is this autoregressive graph generation. And so this is where instead of just kind of putting a bunch of atoms together and then connecting them in different ways, let's predict some sort of molecular core and then systematically build outward from it. Historically, this seems to have been a little bit more successful at generating diverse compounds with molecularly valid properties. And the reason for this is somewhat intuitive, right? Because of course, we're basically taking some sort of molecular fragment that is valid and then continuing to build on it in valid ways. And so by doing this, it's a bit easier to kind of conceive of a way to design a model that's going to generally always lead us with a valid molecular structure at the end. Okay. So the third representation is 3-dimensional coordinates. And so here, I don't have quite as many pretty pictures, but I kind of still thought of this as fitting into these two bins. In this case, this is going to be a little bit more to the stuff that we've talked about in the previous talk, so I won't go into this as much, but basically we can think of either generating, again, the three-dimensional structure in a kind of one-shot fashion, and then using an energy kind of function or kind of a diffusion function to fine-tune those coordinates. Or alternatively, there have been methods where instead you basically assign three-dimensional coordinates to one part of the molecule, and then you basically proceed through the rest of the molecule systematically, trying to come up with three-dimensional coordinates that fit your distribution. And so one example of that is the GMOL paper that's from a few years ago. Okay. So now that we've got some tools for generating these different types of representations, how do we actually train a neural network to learn a distribution? And so again, I think these are things that have sort of come up already as we've thought about simulations and different representations. But our objective here is we want a model that's going to generate data such that the distribution of the generated data as closely as possible matches the distribution of the input data. And so there are a couple of different strategies that we can take to do this. One of them, and I would say this is one of the most common methods of doing this for, especially for two-dimensional and one-dimensional molecular representations, is variational autoencoders. And so this is where we're really interested in learning the parameters of a normalized function that's going to approximate this probability distribution. So we're effectively encoding our molecule into this continuous latent space. We're performing this variational sampling, and then we're decoding this, again, often using this kind of autoregressive sort of molecule building decoder kind of strategy. Another methodology we could use that's related is a normalizing flow model. And so this is where we're instead going to learn the parameters of a series of invertible normalized transformations. And so because they're invertible, we can kind of learn that forward flow. And then afterward, we can apply the inverse flow in order to get our molecule back. A third methodology that we can use is a generative adversarial network. And so this is where instead of trying to actually learn the distribution directly, we're just going to basically pit a generator and discriminator against each other, right? So we will have some noise, we'll have a generator that's going to generate examples of molecules from the noise, and then we will compare that generated data to real training data and have a discriminator that is going to try to guess whether or not a given example is false or true. And then by pitting these two models against each other, we're going to get a generator that's really good at maybe representing our molecular distribution. I think what's kind of interesting here is that the generative adversarial network is kind of nice because it doesn't actually explicitly capture this kind of reconstruction loss that maybe the variational autoencoder captures, but instead kind of is able to learn like a looser definition of what it means to follow the distribution. Another type of generative model that, if I'm honest, I didn't actually focus on as much when I was a postdoc, but has become particularly popular in recent years is these diffusion models. And so this is where we basically have some sort of, it's usually more commonly applied to three-dimensional representations of molecules. And so this is where we're going to have a three-dimensional representation. We're going to continuously add noise, and then we're going to learn the transformation associated with removing that noise and apply that transformation repeatedly. And so we've kind of heard a lot about that in some of these previous presentations in this workshop. And then one final category of generative model that's been used a bit for molecular discovery that I think is really worth thinking about is reaction-based generators. So reaction-based generators really aren't trying to meet this objective, right? They're not trying to match a specific distribution, but basically what they do is they're interested in trying to discover compounds that maybe meet a certain goal by utilizing existing forward reaction models. So as a prerequisite, we usually need to have already built a model that, given a set of reactants, can predict products that can come from those reactants. So this is going to be something that's trained on like a labeled reaction database. And then once you have that model, the idea is that we can kind of string this together and basically stack valid reactions together to get a synthetic pathway. And so in some sense, this is another way of sort of building out a molecule. And so hopefully maybe we'll hear more about that in one of the later talks, because I think there's another talk later today that's a little bit more on synthesis prediction. And so kind of as I'm highlighting here at the bottom, again, this really doesn't learn the distribution of molecules, but instead the distribution is going to be governed by the reactions that are known by the forward reaction model. And forces synthesizability. It also, in theory, could limit your chemical space, because if you're pretty bad at making a certain type of model with your prerequisite molecule, then you're probably not going to be able to explore those molecular configurations. So definitely some pros and cons. Okay, so now that we've got a couple of different strategies that we can take to generate molecules, how can we apply this to the specific question of molecular discovery? So at its core, molecular discovery is an optimization problem, right? So when we as maybe chemists or chemical engineers try to think about what is the process of actually coming up with a molecule, usually what it is some humans are sitting in a room trying to think creatively about how molecular structure connects to maybe some function. Realistically, it's probably some set of functions. And so when we say molecular discovery using generative AI, we're basically trying to replace this process with some sort of automated tool, or at least aid this process with some sort of automated tool. And so to turn this into an algorithmically well-defined problem, what we need is to define a design space. We need algorithms that will allow us to make moves in that design space. And then we need an objective function that's going to guide those algorithms. So starting with these two questions, a design space and how to make moves in that design space, the thing is, a molecular design space is inherently discontinuous, right? So when we make changes to molecules, these are discrete changes that we're making. But one of the advantages to using a lot of these different generative models is that we can map these discrete molecules into a continuous space, with the idea being that if we make kind of continuous moves in this continuous space, that it's going to map back to meaningfully different molecules, hopefully, in our discrete space. And so with this in mind, there are a few different kind of optimization methods that we can use. This is not exhaustive, but these are some of the most common ones. The first one I want to highlight is genetic algorithms, and maybe this is because at my core, I'm a chemical engineer. I'm not really a true AI person. So I think it's worth kind of stepping back before neural networks and thinking about, well, what have people historically been using? And the answer to that is genetic algorithms. So genetic algorithms work on this premise where we have maybe a whole pool of molecules, and we maybe want to predict their properties and decide which of those molecules are going to be the most promising for a specific application. So we use this predictor to basically kind of remove things that we think, you know what, those aren't that promising. We get a sort of smaller pool. And then we're going to apply this kind of mutator function, which is basically going to make these discrete changes to molecules and grow our pool back up from those already promising molecules. And so by performing this iteratively, we're going to get a pool of molecules that hopefully has more desirable properties than our initial pool of our initial pool of molecules. And so one of the reasons I want to start by highlighting this is because this actually doesn't require a continuous design space. We can do this with any discrete problem, right? And so I think this has been part of why genetic algorithms have been useful even when we're not necessarily using a generative model. Another kind of more common technique, once we're using the actual continuous design spaces, is Bayesian optimization. And so this is where we're going to use a predictor that maybe actually is able to give us some sort of prior, so something like a Gaussian process regression or something. And then effectively what we can do is Bayesian optimization to find property optimum in our latent space. And so this is what is probably most commonly associated with things like variational autoencoders. And then a third optimization method, which is also pretty common, is reinforcement learning. And so I kind of alluded to this particularly being used associated with the reaction of the reaction-based generative models. So this is where we basically have some sort of methodology that's going to generate new molecules. We have some sort of predictor that tells us whether those molecules are good. We get a reward, and we use that to update our generator. Okay, so we've got a way to define our design space. We've got algorithms for making moves in that design space. Now the question becomes, well, okay, how do we actually tell our algorithm what moves are useful to make? What does our objective function look like? And so the first thing I kind of want to highlight here is that in real life, molecular design problems are always multi-objective in nature, right? We never really have single objective optimizations that we want to do. And the reason why I say this is, so during my postdoc, I worked on a particular example of trying to discover dye compounds with specific, that would fluoresce at specific colors or absorb light at specific colors. In this case, this is wavelength of max absorption. So what's the color of the dye effectively? But kind of hiding in this, we also needed that dye to be synthetically feasible, right? It wasn't really useful if we discover a compound and we can't actually make it in the lab. We needed it to be stable. So particularly if it's a dye, it's got to be photostable, right? If you can't expose it to light, then why are you making a dye? And then it's also got to be non-toxic. And so I guess this is maybe not trivial, but realistically, for most applications you can come up with for dyes or for really anything else, right? Either you're sticking them in a human body, or even if you're just sticking them in a piece of clothing, right? You don't want them to be toxic. And so in this way, something that was kind of a simplistic overall design problem actually had a lot of important objectives hiding in it. And this is really true of effectively every real world application we might be interested in. And so I want to highlight this because when we think about applying generative models to molecular discovery, we do have to reckon with this, right? So we can think about objectives as being single objective optimization, but more commonly, we have to think about multi-objective optimization. And so here I'm trying to kind of draw a schematic that makes it look like we can do explicit multi-objective optimization. And in the best case scenario, this is what we would want to do, right? So if we have an approach to maybe have a predictor for a wavelength of maximum absorption, but we also have robust predictors for synthetic feasibility, stability, and toxicity, then the best thing to do would be to put it all together and come up with an objective function that's going to be able to combine all of these things. But in a lot of cases, we don't actually have strong predictive models for every possible objective that we might be interested in. And so a third kind of strategy that I want to highlight is this idea of indirect multi-objective optimization. And so this is where maybe you have one or maybe two objectives that you're particularly interested in, and maybe you've gone to the trouble of building a really good predictive model for those applications, but you kind of know there are a bunch of other problems. So things like maybe stability, where you haven't built a really good model, but you know you're going to have to worry about that when it comes to actually utilizing that molecule, commercializing it, or whatever your end goal is. And so in this case, we might be interested in doing this indirect multi-objective optimization where we somehow constrain our overall search in a way that we believe is going to be connected to those secondary molecular discovery requirements. And effectively, we're going to limit our search space. Okay, so what does this actually look like? So there are a few different strategies that I'm kind of alluding to that we can take to optimize molecules. So the first is going to be property constrained molecular generation. And so this is where we will explicitly represent all of our objectives during molecular discovery. The second I'm going to define as structure constrained molecular generation. And so this is where we're going to generate an example that follows a learned distribution from a seed. And so the idea is that maybe we have some sort of scaffold or some sort of region of a molecule that contains properties that we already know we like. So it could be, if we're doing drug discovery, it could be that we already know that some portion of the molecule is going to be active. It's going to bind to some sort of pocket in a protein. If it's a dye, for example, it could be that we already know that a certain dye core has some sort of fluorescent properties, and we kind of want to preserve that. And then maybe we're trying to engineer other properties around that molecular structure. And so there's a lot of literature in this, but I think it's kind of important to recognize that the goal of doing this structure-constrained molecular generation is to preserve certain desirable properties that maybe we can't explicitly control during the optimization process. And then the third strategy that I want to highlight is unconstrained molecular generation. And so this is where instead of saying, hey, I'm going to constrain my generation process using property prediction models, you're just saying, hey, you know what? I'm not sure if I really believe my property prediction models that much. I'm just going to generate a ton of new examples. And maybe practically, if I'm trying to do this in a molecular discovery setting, I'm probably going to apply my property prediction models later as either filters or as kind of prioritization in an active learning workflow. And so a lot of the times, actually, unconstrained molecular generation can practically make a lot of sense, right? Because we can wind up with potentially a lot more molecular diversity if we don't necessarily believe our property prediction model is that strong. And so to kind of hit this home a little bit more, with property constrained molecular generation, we're treating the primary objective explicitly. Same with structure constrained molecular generation, but with unconstrained molecular generation, we're maybe treating this primary objective as a filter. And then with the additional objectives, we're going to have to explicitly treat them in property constrained molecular generation. Whereas with structure constrained molecular generation, we're treating it implicitly. And with unconstrained generation, we might again treat these as filters. Sorry, I have a block on my screen that's preventing me from seeing my slides. Okay. Okay, so I want to dig a little bit more into this idea of structure-constrained molecular generation, partially because I think it's a really interesting approach, and also because I've done more of it. So the goal with structure-constrained molecular generation is that we want to take an input scaffold or structure and build on it to generate a new example. And so in this way, structure-constrained molecular generation can actually be unconstrained in the sense that we don't necessarily have to tie it to a property, or if we have a particular property that we want to optimize over and we really feel good about that property prediction model, then we can do it in a property constrained manner. And so there are a few different kind of categories of ways that we can do this. We can do this as scaffold or fragment expansion. So this is where maybe you have some sort of molecular core and you're going to try to keep adding different molecular pieces to it in order to create a bigger molecule. There are also a number of strategies that fall under this banner of scaffold or fragment merging. So this is where maybe instead you have multiple properties that you're interested in engineering your molecule with, and you're going to take fragments that correspond to these different properties that you're interested in and come up with different ways of merging them into different kinds of molecules. And then the third is molecular translation. And so this is where instead we kind of think about molecular discovery as a translation problem, similar to, like language translation. And we're basically thinking about this as the problem where we're trying to translate less optimal molecules into more optimal molecules. So we're effectively trying to train a neural network that's going to take in a given example of a molecule that maybe has some properties that we like, but we maybe want to improve one specific property. So something like we could be interested in improving activity for a catalyst. We could be interested in improving solubility, perhaps, for a drug molecule, et cetera. Okay. So I also wanted to take a moment to talk a little bit about molecular generation benchmarks, because of course I've mentioned a lot of different methodologies. And so the question maybe becomes, well, how do we actually sift through all of these papers that you see coming out from, NeurIPS and ICML every year and decide which one you're actually going to use? So benchmarks, and this is maybe a more philosophical point, are great because they facilitate the participation of people who are more in the modeling field, right? People who don't necessarily have domain expertise, by providing a unified objective that we can try to achieve. And you don't really need to understand the motivation or the context deeply to know that you're contributing to maybe an important problem. And on the flip side, it facilitates the participation of the domain experts by providing kind of a leaderboard, right? Like you can look at benchmarks, and as long as you see which, which model has the best, performs the best on benchmarks, you can just pick that and move forward. And so benchmarks are a nice, convenient tool. However, many generative modeling benchmarks have now regularly maximized most methods. And this has really caused researchers to express the need for better benchmarks in the generative modeling space. It's become really difficult to practically know which generative models are better than others. My personal opinion on this is that part of this is that generative models generally work at this point. We have a lot of different flavors. Some might be a little bit better at some things than others, but my opinion is that a lot of the time, the choices you're going to make in terms of which model you use are going to be more guided by the strength and robustness of your property prediction models and the other constraints on your molecular discovery process. But I think this is something that is maybe not well captured by the idea of benchmarks, which, people keep publishing papers and trying to beat. But I did want to take a moment to kind of highlight what these benchmarks are, because if you're reading these papers, you're probably going to see them and wonder what they are. And so in the unconstrained molecular generation space, we have a number of benchmarks that are really focused on the quality of the molecules that you're generating. And so the way that we define quality is going to be focused on validity, things that pass filters, and things that are unique. So obviously, if you keep generating the same molecules over and over and they're literally identical, that's not a good generative model. And also, if you're generating molecules that are invalid, so usually we define validity related to whether or not a molecule obeys kind of basic valence rules, right? Does carbon make 4 bonds? Then, that would be, if it doesn't, that's not necessarily going to be a valid molecule. So another category of benchmarks are this distribution learning benchmarks. And so this can kind of fall into a few categories. Here I'm pulling out KL divergence and distributions in terms of a few different molecular property distributions. And so basically the goal here is to evaluate these molecular generation models on the basis of how good they are at being able to learn the training set distribution. And then another category is novelty. So of course, if our whole goal is to use molecular generation for molecular discovery, then presumably we want to come up with molecules that are pretty novel and in a dream setting are coming up with something maybe we wouldn't have come up with ourselves, right? Because if you sat down at the drawing board and you came up with the best molecule immediately, then you probably didn't need an AI tool to help you with it. And so novelty is a pretty big part of the value that generative modeling is supposed to provide us. And so here people generally evaluate novelty on the basis of, well, first, just novelty in terms of molecules not present in the training set. And then we can also evaluate it based on fragment similarity and and scaffold similarity. And then finally, a last category that I want to highlight is this idea of chemical space coverage. And this is kind of an interesting idea. Basically, it's a measure of the extent to which generated molecules cover the space of the GDB13 data set. So the idea that if we've actually defined something that kind of defines a specific chemical space, how well does a generative model actually kind of cover that space? So those are all the unconstrained benchmarks. What about benchmarks associated with actually discovering molecules for specific properties? So goal-oriented benchmarks are really aimed at evaluating just that. But of course, they also have to kind of be fairly straightforward to implement in a diverse number of settings. And so this becomes somewhat of a limitation because they need to be things that can be evaluated kind of cheaply and quickly. And so they wind up being things like this. So similarity, maximizing the similarity to a target molecule. Another one is rediscovery. So trying to discover molecules that maybe minimize the difference between the target molecule and some unknown molecule that the model doesn't know about. Isomer identification. So maybe being able to generate molecules that follow some sort of simple chemical pattern. median molecule discovery, so trying to generate molecules that maximize similarity to multiple molecules. And then this is probably the most similar to real molecular discovery campaigns is calculated property optimization. So this would be the case where maybe you have some sort of property that's straightforward to computationally evaluate. So I think I heard a previous speaker talk about chemical like drug likeness scores, and so that would be what QED is, or computationally evaluated log Ps. I think the caveat here is that these are really kind of computational, artificially generated. And so these are not necessarily going to be the same as a real experimental property. But this is probably the closest to a real molecular discovery campaign kind of problem. Okay, so I've talked a bit about how kind of from a structuring the problem standpoint, we can think about using generative AI to discover new molecules. I want to spend the last part of this talk just talking a little bit about, well, what does this look like in real life and practice? What is kind of the art of using a generative model to actually try to find new molecules? So what do these benchmarks look like for realistic use cases? So quality, for example, and a lot of model systems, we're really just evaluating quality on the basis of valence rules and or syntax. But in a realistic use case, quality can actually depend on a lot of different things, right? Quality might mean a molecule that is synthesizable, something that is not toxic or stable, right? When we think back to the examples of kind of what I called bad molecules on the first slide, some of those molecules actually do obey valence rules. And if they're smiles, they usually also obey syntax. So we were able to get a molecular graph out of those. But if you just look at those, you know that they're not going to be stable compounds. And so in this way, in a realistic scenario, we do have extra quality that we care about when we're trying to actually use these molecules. Novelty is another thing that is not really truly captured. So normally we're evaluating novelty based on Tanimoto distances, or as I mentioned before, this kind of scaffold-based similarities. But in practice, this is often at odds with quality. So if we wind up coming up with a molecule that looks nothing like any molecule anyone's ever seen before, and I've done this, and you hand that to your synthetic chemist collaborator, they're potentially not going to be happy with you because there's going to be no way to actually make that molecule, or it's going to be extremely unstable. And then finally, and this is the one I think that is maybe the most difficult to overcome, is the property optimization. So in a lot of examples in the real literature, we see that properties have been deliberately selected to be computationally cheap. And this makes sense. It makes for benchmarks that are really easily accessible to a wide audience. But in practice, we find that properties that are experimentally evaluated have a lot of other issues, right? So we wind up having error associated with the data itself. We wind up having models that we're training on it, surrogates that we're going to actually use in our modeling approach. And those surrogates are going to also contain some sort of error because we have limited data sets. And, you know, this makes it quite a lot more difficult to actually couple in practice property optimization to generative models. Okay, so one of the kind of caveats or things that we really have to worry about when we're using generative models to discover new molecules is whether or not these molecules are synthesizable. This is probably one of the first questions that we ask when we look at the molecules that are kind of coming out of our model. And so I want to highlight this as a particular kind of caveat that we have to think about. And there are a few different strategies for actually computationally evaluating whether a molecule is synthesizable. But I guess I want to highlight this because this is kind of non-trivial. I won't go into this in too great detail because I know there is a speaker who's talking about it later today. But we have a few strategies. One is computer-aided synthesis planning models, which calculate synthetic pathways for generated molecules. But one caveat here is that these aren't actually that computationally cheap. So to build a synthesis tree for a single molecule is going to potentially take seconds to minutes. And if you've generated on the order of like, you know, millions of compounds, that's somewhat time consuming. Something that's a little bit faster is these synthetic feasibility scores. And so this is where maybe we can calculate some single numerical score that's going to tell us whether or not we're likely to be able to synthesize a molecule. And so these are easy to calculate quickly. And so here are a few different kind of examples, but even these, they have their caveats. In my personal experience using these with generative models can learn to exploit weaknesses in your predictors. And so they find the thing that's wrong with, for example, the SA score. So even though it's a pretty good metric, your generative model might find ways to sneak around it. And then finally, we have reaction-based generators. And so this is where, instead of trying to basically treat this as an optimization problem where synthesizability is a goal, let's just actually bake it into the generator so that the generated molecules not only have a molecular structure, but actually have a pathway to that molecule. And there are a few examples of this. So another thing that I've kind of alluded to that's maybe, in my mind, the other main difficulty associated with using generative models for molecular discovery is that generative modeling workflows rely on predictive models which have inherently limited certainty associated with them. And so I think one of the biggest solutions that people have developed is to incorporate information about uncertainty into your objective function. And so this is maybe where, if you have an objective function and you're interested in not only maybe discovering compounds that are optimize your property, but rather discovering compounds that are going to be able to be useful in kind of an active learning setting. So something that's maybe going to be, you'll be able to use to retrain your model and maximally impact model performance. Then you can kind of implement these generative models into a more active learning workflow. And then this way you can cope with having a predictor that has limited uncertainty. I guess another kind of note, and I guess I've already kind of pointed this out, but I want to hark back to it, is that optimizing a model with bad predictive models actually, directly embedded in your optimization can limit your exploration. And so to some extent, we want to be really deliberate with the way that we combine property prediction models with our generative models, because it will impact the way that we explore the molecular design space. And then finally, one kind of last note that I want to leave you on is this idea that there are maybe kind of two categories of ways that people often use molecular generation in real world applications. The first, in my mind, is forward discovery. And so this is where we'll have some sort of combination of generative and predictive models that are going to give us some sort of set of candidates. In this case, I said 10 to the 4th molecules, but this can be a lot higher than 10 to the 4th. And then we apply some combination of computational and realistically often manual filtering to get down to a small number of feasible molecules that we can synthesize and test. And so the vast majority of examples of using molecular generation in real-world applications generally follow this forward discovery framework. The reason why I highlight this closed-loop discovery framework is because this was one of the problems that myself and a bunch of other postdocs, when I was a postdoc, were working on, and we recently finished, and it was published, and it's pretty cool. So the idea is you basically have a series of these generative and predictive models. They're going to come up with a whole bunch of different molecules, but then we're going to have a fully automated approach for prioritizing and filtering those molecules, coming up with the synthetic pathways, figuring out how to then implement those synthetic pathways in a high throughput experimental platform. We actually had a high throughput experimental platform that then performed the synthesis, characterization, collected all the data, put that back in the predictive models, retrained, reselected new molecules, and did a few different loops of that. And so I just wanted to sort of call out this paper that we recently published in Science back in December, because I just think this is so cool. My piece was this tiny molecular generation bit at the beginning. I'm not going to lie, this robotic piece is really quite hard, probably a lot bigger than what I did. But you can see that basically by combining all of these different pieces, we were able to get this overall closed loop workflow, and we were able to perform 3 levels of optimization over the course of which our property prediction models went from not really knowing the properties very well to actually being very robust, at least in the molecular design space that we were exploring. And so this wound up being a really cool example of what really is closed loop, fully automated molecular discovery. And so with that, I'll kind of end here and take any questions. So I'd like to thank my group. The work that I talked about at the end was really carried out with the Jensen group and actually a whole bunch of other groups at MIT too. So I should call out that. And then a lot of the stuff that I talked about today, we had a review paper that we published a few years, well, 2 years ago, I shouldn't say a few years ago, that was on generative modeling. And so if you're interested in kind of digging more into the details, I encourage you to check that out. Cool.
We can take some questions.
Hello, thank you for the presentation. I would like to ask, what are the, in your opinion, best tools in open source that you have, for generative drug design? Is it AstraZeneca's reInvent library, or do you know any other better frameworks? Or maybe not specifically, let's say, not covering the whole space of generative modeling, but let's say a specific, let's say, models that you think is the best in 2024? Like, what is the state of the art of
the state of the art? I guess, I mean, I guess this kind of gets back to what I was saying about the benchmarks. I think one of the tricky things in this space is, in my mind, like, we kind of got to a point really a few years ago now that most models were pretty comparable. I think there are probably some models that are worse than other models, but I'd say a lot of models are tied for state of the art. And so you might see that one is better or another, but I think practically, I think practically there winds up not necessarily being a huge difference, is my opinion, having tried a number of different methods. And so in my mind, I would recommend for anyone who's interested in using generative models to think more about what is straightforward to implement, and also think about how you're going to combine your property prediction model with the generative model, because in my mind, that's going to be a little bit more impactful in terms of just determining your level of success.
Thank you very much for the really great talk. My question is about reaction-based generators. I'm not a chemist, but I imagine that every year, maybe even every month, there is new chemistry came out because a lot of people working on new chemistries. My question is how fast should be this reaction-based generators be updated? And do you know if there is validation, because some chemistry may be not reproducible, etc., to just keep up that you're not restrain your generative model in terms of that you mentioned that you can generate, but maybe someone just came up with just synthesis that's make it possible.
Yeah, I think that's a great question. So I guess to be fair, Connor, who will be speaking later, probably should add to that question, whatever my answer is. But yeah, my impression is this is probably one of the drawbacks to using a reaction-based generator, right? It's difficult to maybe curate those data sets. There are some efforts going on right now that he's involved in related to curating those data sets, but there is a fair lag time associated with it. It's not just like someone publishes a paper and it magically gets pulled in, I think. And so that's one thing to think about. And then the other thing to think about is that you also do have to worry about the fact that if there's certain kind of classes of molecules where your forward reaction models don't really do a good job of building those, then you won't necessarily be able to sample very well in that space. So I think the example that comes to mind is that at the time that I was working on this dye project, so of course dye compounds often have these kind of highly conjugated ring structures. And so we were trying to explore basically doing, synthesis pathway prediction for these ring structures. And I think there have been papers that have kind of focused on improving this, but at least at the time, it was very difficult to do forward prediction of ring forming reactions. And so that would be kind of an example of maybe a class of reactions where, you know, if you were using that embedded into your generator, you probably would wind up with a generator that just couldn't really form highly conjugated rings, which for this application would have been really bad. But then again, you know, I think that's the kind of thing that I think is being continually improved. So I think while that might be a limitation, it's probably the kind of limitation that folks will be able to kind of overcome in the next few years, and maybe already have, I don't know. Yeah.
Thank you for the great talk. I had a question about I think it was called scaffold-based generation. I think one of the speakers before talked about this idea of activity cliff. I've also heard of the concept of SAR paradox. I was just wondering how that affects the generative approaches that you discussed today.
Yeah, so I guess by activity cliff, you effectively mean like a very small change in the molecule results in a really large change in the property. And I think that is generally a very large difficulty with these methodologies in general. I guess somewhat the idea would be that in theory, in an ideal world, but you would be able to learn some sort of latent representation where maybe, yes, a small change in molecular structure would lead to a large change in the property, but maybe your latent representation is kind of holding the important information. And so maybe your latent space doesn't contain those cliffs quite as much. I think practically people don't, I've seen a few papers that try to go after that. I think practically people don't really worry about that. And I think at the end of the day, like your model just has to kind of figure it out. I think it's problems that have more activity cliffs are just harder. Yeah, sorry.
Thanks for the great talk. I had two questions. So one was with respect to the multi-objective strategies, and you talked about how objectives can be treated implicitly. Could you speak to that a little bit more and what that practically looks like? And then my second question is, sometimes when you are doing multi-objective optimization, having more objectives makes it basically harder to find your minimum in the loss landscape. Are there certain strategies for optimization that work better for higher numbers of objectives?
Oh, that's a good question. Okay, so I'll answer this first question first about implicit kind of multi-objective optimization. So maybe I didn't jump on this quite as hard, but I actually view structure constrained molecular generation as in some sense this kind of implicit generation, or sorry, implicit multi-objective, because the idea being that your structure, your strategy for structurally constraining your search is actually implicitly trying to capture specific properties, right? So if you're trying to do an exploration around a specific fragment or set of fragments, then the idea is that there's something about those fragments that you desire and want to keep as a feature in your kind of molecule. And so that's one strategy. Maybe like less sophisticated strategy would just be to say, and this is easy to kind of imagine using maybe genetic algorithms, but there's probably other ways to imagine it, is to say, okay, I'm going to actually take maybe a population of molecules or something, and then I'm going to do sort of a local exploration around that population of molecules. So one of the things that I did during my postdoc was we were interested in applying molecular translation to basically do sort of an exploration in a population of molecules. And so what we did was we applied molecular translation in sort of a genetic algorithm framework so that we had kind of a population that we would keep kind of mutating, but using molecular translation. So we're mutating it in the direction of some sort of property optimum. And so by doing that, we're sort of anchoring our search to an initial population that has qualities that we are interested in caring about, but we're still trying to optimize for specific well-defined properties. And so your second question was, can you remind me what your second question was?
Oh, yes. It was when you have a high number of objectives, are there certain optimization strategies that work better than others?
Yes. So I guess my short answer is probably, but I'm not 100% aware of them, so I apologize for that. And so I guess then the other thing is that in my personal experience, I'll say that, as I said before, I've found that one of the issues I've had associated with finding optima from multiple objectives is that I never have had at my disposal property predictors that are so good that the error in the property predictor doesn't become the problem. Because a lot of the times, if I have basically multiple properties and I'm trying to optimize them all at the same time and trying to find like a population of molecules that really match that optimum, a lot of the times I, in practice, am finding molecules that are effectively finding the gaps and holes in my models, right? And so I think if you have near perfect property predictors, there probably are like optimization schemes that are well suited to that, but I think that's just a problem I personally haven't encountered.
Thanks very much.
Let's thank the speaker again. And if you have any further question for Dr. Bilodeau, you can ask online.